Oh. Okay, can you hear me? No, no, no. Can you hear me? Hello, good afternoon. Yes, you can hear me. Okay, I cannot hear you yet.
Can I hear us?
Oh, yes, I can. Thank you very much. Okay, and
No problem, Coach.
all right, and I cannot see. Oh, and then my hand. Coming. This problem will require a little. Okay, so all right, so I can hear you. I can hear you here. All right, we did the wave speed yesterday. All right, I'm gonna, oh, wait, sorry. I think we're ready to go. Hold on a second. Yeah, this board, what's up is the problem. Okay, but I will have to explain this problem, like this. Oh, quick question before have you guys done, you have not done the Doppler effect in lab yet, right? Like you on lab, or you're on lab 4, right? Or hello? Looking at the chat. Hello, wait, you guys can hear me, right? Oh, we just started lab 4. Okay, right, thank you. Started lab 4. Okay, laptop. Okay, perfect. We're gonna get to that today. All right, there's still people coming. Blah, blah, blah. Okay, and oh, I actually can't see you. Can I see? Can you see me? I don't know. Okay. Now, oh, okay. All right. All right. Let me explain the. All right. So we're just going to keep going the way we've been going. There's like the point system, the 50-point thing is getting increasingly complexified and gamified and hopefully funified, hopefully. And we'll have a review, a practice thingy soon. But the right where we left off yesterday, or 2 days ago, was wave speed. Like and now I want to take the speed of a wave super seriously. Like the big point of yesterday was Okay, I'm sorry. So what we're saying is this equation, so this is a very powerful equation. This is a very big deal equation. It is not we keep talking about it like, and it's not an example of 85 different equations that you would ever have to know on an exam or like in this subject of physics. It's like the equation of a certain topic. It's the second order differential equation that captures the essence of any wave motion at all in the universe. Any, sorry, this is getting a little difficult. Excuse me. Any, to be strict, any one-dimensional wave motion, by which I mean, and that's a misleading term. What we really mean is any wave ripple within a one-dimensional medium. I might have to write that in a moment, actually. But we mean if you picture a string and ripples are going along the string, or you picture a column of air, like in a clarinet or a flute or something, and ripples are going along the column of air, and we call that sound. So whether the ripples are like, blah, 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 like we always sort of draw squiggles on a piece of paper, we call those transverse, or the ripples are boop, 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 like pulses, compression pulses, like slinky ripples, and those are called compression waves or longitudinal waves. The shape, either way, if you have a pulse traveling along a one-dimensional medium, then this equation captures everything that is necessary and sufficient to characterize that pulse. Anything that satisfies this equation is a pulse, is an immaterial thing traveling down a one-dimensional medium. Like that's already, and it's a relationship of derivatives. Okay, I have to keep emphasizing it, and I know again it's always like, God, like when we get to the exam, it's going to be 85 different equations, or next science course, there's going to be all like, why are we spending so much time on one equation? But just so you know, like the Schrodinger equation of quantum mechanics, of all of quantum mechanics, like the F equals ma of all of 20th century physics, and the heart of the equation of pchem, like which everybody has to take usually next, all comes down to a slightly more complicated version of this thing. Like this is the centerpiece of atomic physics and everything in the world that isn't like a piece of matter moving along through space, honestly. Like, and everything of that is described by F equals ma, which is also actually a differential equation. But so this thing is like a big deal, and it is a lot of information that it contains, like derivatives of two different kinds, and then this constant in the parentheses, which is what we really were trying to unpack or analyze yesterday. Now I want to talk more about this constant in the parentheses, omega squared over k squared. By definition, what we were saying yesterday, and this is what I'm trying to remind you right here. I guess I'm like really lecturing right now. Sorry. We will get back to the problem in a second, but I need to tell you this. By definition, like we were saying yesterday, omega is angular frequency. That's like cycles measured in radians. Okay, so it's like cycle portions per time, and k is cycle portions per space, right? Each one of them is like a rate in time and in space, and you put one over the other, and then it's like a fraction over a fraction, so the denominators flip. And what we have there, by definition, is it's cycles per time. Sorry, since it's time per cycles over space per cycles, it all flips, and you get space per cycle divided by time per cycle. Like what omega over k really just is, oh, if you track a certain piece of this wave with your eye, and I always stutter when I say that, because you can't track a wave, right? A wave is this whole phenomenon. A wave, there's waves in the ocean. There's really no such thing as a wave. There's a phenomenon, and you can track with your eye a wave crest or something like that. And that's what I'm talking about right now. We're doing, but just remember, when you're tracking a wave crest with your eye, a particular trough that you've set on in your eye, you're tracking just a disturbance in the medium. You're following with your eye just a temporary misshapenness in the medium, whatever the medium is. And that's where, but then that thing carries information in it, that disturbance. So if you track that with your eye, a wave pulse, we're saying that it goes at a speed, which is this here constant term. In other words, this whole wave equation can be written more simply. And I'm still talking, sorry, I will try some. But we're saying an easier way, like that everything that is true about a wave pulse is captured right here. Okay, where like okay, just to remind us again, oops, sorry, some of that, yeah, oh, sorry. Hang on. Just to remind us, so this wave equation, which must be true at every single point in time and every single point in space, or any single point in time and any single point in space that you pick for any, if you're looking at the ocean, you're saying there's waves there, if you say the whole surface of the water is described by waves, or if you say ripples are going back and forth on a string that you and your lab partner are holding, then at any and every single point in time and space, this whole relationship must hold true. And the relationship, again, is like if you picked some little bit of some little hump, the rate at which that little bit of the hump is accelerating back to the equilibrium flat one-dimensional axis, the rate at which some little bit is accelerating back to the axis is directly proportional to how curved, how concave, how bent, how disturbed the medium is at that point. The more disturbance, the less flat, the faster things accelerate back to home. Like that's what wave motion is, but one is directly proportional to the other. Acceleration along the vertical axis is directly proportional to concavity at that point on the vertical axis. The constant of proportionality now, we're saying, and here's where I want to start pushing it forward, we're saying happens to be now the square of the horizontal speed of propagation of this pulse. We're saying like this is like related, is directly proportional to this over here. And they produce this pulse that goes like this, whose rate is the square root of that constant, right? Like it's weird that it's all tied together that way, but it is. But now, if that V here is actually a constant, this is what I want to say now, back to this page. If V squared is omega squared over K squared, and if omega and K they're not just constant, like, well, I mean, they're constant, but they're not just constant arbitrarily because we like mathematically set them so. They're constant, remember omega is a parameter of simple harmonic oscillation. Like omega is the rate at which any little bit is cycling back and forth along a vertical axis. It's the cycling rate is what omega is. Where did that come from? Well, if this little thing is an oscillator, think of it as a mass on a spring. Remember, I guess what I'm saying is, remember, I know I'm just talking and talking here. It's almost like class. Like omega is defined to be 2 pi over t or whatever, that's its definition, but what it turns out to be in harmonic oscillation was something like this, different k, the other k, right? The Hooke's law k. So I'm not putting the serifs on it or whatever. What does this mean? Remember, so I'm saying something that we've said like a month ago, and I personally thought it was really interesting then, I think. But now I want to say why it figures in, and it's interesting again in a new way. Like
if you remember that a typical mass on a spring oscillates back and forth at a cycling rate that is fixed and determined by spring stiffness over spring mass, like square rooted. In other words, the cycling rate, if you remember that omega equals square root of k over m, and like k over m is in the simplest case of an actual mass over on a spring, but if you look at any other oscillator like a pendulum bob on a string, or any system that satisfies our original differential equation for harmonic oscillation, anything that is a harmonic oscillator, what we said and made a big deal of then is that its oscillation rate in time doesn't depend on space. That was our point. Like and this is like the whole essence of a clock. You can take the mass in the spring, set it all up, and you can set it up from here, let it go from here, and it makes big swings. Or you can set it up from like just pull it a little bit and set it up so it makes little swings. But whether it makes big spatial swings or little spatial swings, whether it covers a big amplitude of distance or a small amplitude of distance for each one of its swings, it turns out that its swings will always take the same amount of time no matter what. Big swings take the same amount of time, remember, and it's a really big deal. It's what it means to be a clock, that big swings take the same amount of time as even little swings. They all take the exact same amount of time, of like t, the period, the inverse of the frequency, which is the 2 pi over this, right? They all take the same amount of time because and I would never think that. I would think, what, big swings would take more time. Like, are you kidding me? Like, you have to run all the way there and run all the way back. Of course, that's going to take more time than if you just have to run from there to there. But if you pull all these are harmonic oscillators. If you pull something way back over here, if you pull it back here to a much farther distance, and say now you have to travel a much farther distance for each of your cycles, oh wait, okay, I'll read the handwriting in a second. Sorry, I'm just going to finish my sputtering here, and then I'll read the handwriting. Then I'll pretend I'm not in a Halloween costume for more time. If you pull the thing all the way over here, it has an enormously greater amount of potential energy, remember, like Hooke's law, all that. And so you let it go from here, so it has a lot more potential energy to convert into kinetic energy. So on average, it has a lot more kinetic energy. And lo and behold, the big swings go much faster on average than the smaller ones by exactly the right amount, always, so that it always works out that, and then I'm going to get to Rain's question, sorry, the handwriting thing. But that, just remember, everybody, like harmonic oscillator, one harmonic oscillator, if it's oscillating harmonically, it means not only is its cycling rate constant, like steady, like you can measure it and rely on it, but like it's not even dependent on how far on how you set it up. It's only dependent on its material ingredients, stiffness and mass. Cycling rate is. And K is the same exact thing. So what I'm just saying here, well, okay, so to Rain, wait, sorry, I'm losing my mind. Oh, between is and determined. Oh, on that page, sorry. Between, no. Oh, is entirely. I'm sorry, entirely. I'm an axe murderer. No, I'm a warlock. No, I'm so what I'm trying to say right now, the good point, right? And that's no, thank you. And that's like 50,000 million. Oh, there was an LOL. So someone actually did. Yeah. So I'm in a Halloween. Yeah, I'm in a, right. Okay. Thank you for the acknowledgement. I was wondering how long I had to do, and it's not just, okay. Right. So I'm glad that we all noticed that. That's how much I care. But what it says here is the constant omega is entirely determined by material properties. That's a reminder of something that was true even if we were just analyzing one oscillator, and it was the definition of a clock, really, like harmonic means that your constant frequency, angular frequency, frequency period, the whole package, that constancy of that was determined from the get-go when you were put down on the table as a little piece of spring next to a little piece of mass. Like once the spring was picked out and the mass chunk was picked out, no matter what you do with the system, pull it, stretch it, it's going to have that ticking rate. Like we've been saying that. Now I say, well, if that's true, and if K is the same thing, K is just angular, is ticking rate in space rather than time, omega and K are determined by material. So the constant. Like omega is abstract. It's a hard thing to get your head around, but we're getting more and more used to it, hopefully. Then K came along, and it's a little harder than omega for many of us. But remember, K is to space whatever omega is to time, and omega is a cycling rate in time. And we've been saying so we're saying that any given spring is just going to do what it does. You put it down. Now we put a whole bunch of springs down. I'm totally lecturing. Sorry. We have a whole bunch of springs, like a whole bunch of vertical springs, all stretched out in a horizontal assemblage, like ensemble, like collection, a whole horizontal collection of vertical oscillators, all like kind of like piano keys, and they're all going bit, 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 but they're all going like in staggered phase, right? I.e., it's a wave pulse. It's a ripple that's pulsing through. What we're now saying is, oh, the speed of that ripple, the speed, the omega over k, the rate of the pulse is entirely determined from the get-go by what these oscillators are made out of. So okay, this means, so anytime you send a ripple, anytime you send an immaterial thing, like again, a wave pulse is what we're studying here, which is a non-thingy thing. It's just a pulse. It's a wiggle. If you send a wiggle down a string from me to you, or you send a wiggle through air molecules from my mouth to your ears, and again, remember, that means you're sending a wiggle. You're not sending any air molecule, right? But if you imagine a wave pulse going from somewhere to somewhere else, the pulse is, there are things pulsing, right? Like if it's a sound, then it's air molecules vibrating. If it's a slinky pulse, then it's pieces of metal in the slinky vibrating back and forth. That entire, all of them vibrating harmonically. Now, this entire collection of harmonic oscillators is what we call the medium. The medium is the materials through which the immaterial thing flows. Okay, like there has to be something material to which this is all tethered. Otherwise, it's like not science. Otherwise, it's witchcraft. But it is science. So there's a material basis to everything that's happening. But what's happening is a bunch of little materials are all dancing in a formation. They're all oscillating in time and space perfectly, so that like all oscillating perfectly in vertical time, so that a horizontal pulse goes like this. We're now saying that the speed of that pulse is entirely fixed from the get-go by just the nature, the material properties, like the size of all of the material of the medium of this collection of materials. In other words, if you send a ripple through water, if it's water, like in a tub, it's water at a certain temperature, at a certain pressure, with maybe a certain amount of salt in it or whatever. It is, and it is water with material properties. that means it's a bunch of air molecules that are each identical, identifiable, measurable air molecules, each one of them sitting there acting like a little mass on a spring, maybe in 3 dimensions or something instead of 1 or something like that. But each one is a little mass on a spring. And once you say it's an air molecule at this temperature and this, then you know exactly, in effect, the stiffness of that spring. You know it's K and M. It's going to vibrate at one and only one natural frequency. It's omega. So you want to send ripples through water. If you fix the water, the ripples go at one and only one speed is what we're saying. This is a really big deal, honestly. This is a really big deal. I mean, of course, I want to get back to the math and everything, but I cannot emphasize enough how bizarre and like both practically important and also mystifying this is. I mean, it's not mystifying because it makes sense, but it's like miraculous that it all comes together to make this kind of sense. What I'm saying is, so let's go back to like, and again, I know I've got to ask but the problem I want to ask about this, the topic where this is going is why such crazy things in the world happen as the Doppler effect, which actually is a crazy thing based on this. I mean, it happens all the time. Doppler effect is like, that business. We're using this to analyze that business of like when a car goes past you and then the sound changes to your ear, like that little effect called the Doppler effect, which happens because of this. That's actually how we know the universe is expanding. So this stuff is like a big deal. And the thing that I'm saying right now is, if I hold a string, one end of a string, and you hold the other, like supposedly in lab 3 or whatnot, if we're all, or some simulation there on 2, if we're each holding one end of a long string and you're like flicking your end up and down so that ripples go back and forth to me, which is nice. So you send ripples on. Or again, if you don't like that, you could just picture like tapping like the surface of water with a stick so that ripples go out. I mean, that may be more dimensions than one, but picture some kind of like ripple going back and forth steadily, right? Okay, now, and you're making the ripple. What we're saying here is you can do whatever you want. Like you can start shaking your hand a lot more, so you make a lot more ripples, i.e. you can totally play with the frequency of a wave. You can play with the frequency. You can make it go like ripple, 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 ripple. Or you can make the frequency really low, ripple, crest, crest. But what you can't play with at all is the rate at which any one of those crests journeys from you to your partner. Like you can make a lot of crests per second. That's called a high frequency. You can go like this. Or you can make low frequency. But you can't change, but that's how many you're making per second. That's cycles per second. Meters per second is totally determined by omega and K, which is just the material that the string is made of. Nothing, so you cannot do anything to this material. I mean, you could like bend it out of shape or something. But if you just do anything natural to make a pulse, the material fixes the speed in the same way that the material of a spring fixes the vibration rate. So once we say medium, like, oh, it's a piece of string between my lab partner and me, waves are going to travel back and forth along that string. Not only are they not going to accelerate, like they're not going to speed up, they're not going to slow down. All the hard physics of acceleration we spend half of physics 203 doing, we never have to apply to wave pulses because they just go along at a steady rate. But not only that, you can't even change that rate by sending them differently. Like their rate is constant in time and constant in space. Everywhere in that medium, the ripples will all go the same way. The last way I'm going to put it, again, it's anything we say in physics always seems obvious once you say like, oh, waves go at a constant speed. But this is like why we like waves so much, because once you create a wave and you send a ripple from me to you, all you got to do is know what kind of ripple you're sending, and you'll automatically know exactly how fast it's going to go. And it's going to, and put one last way, if you're ever standing and you see ripples anywhere, if you're standing at the beach and you see big waves coming in, or you're in a pond and you just see like ripples going around and you make ripples, or you look in a bathtub, like this is a really weird thing. You've probably stared at ripples your whole life, and maybe you're even looking at a wave tank later in lab in this class or something, and you certainly will in other classes if we ever have classes. But one day after you hear me say this, actually stare at the ripples, and you'll notice something about this so completely obvious. Well, here, it's so obvious, except it's so not. Like even just when people draw ripples, like okay, hold on. I know I'm just talking now. I get too excited about this. I really do get excited about this. Hold on. So, I mean, even in like a stupid drawing, which that is, of just imagining like someone dropped a rock in a pond. Okay, this is this is a very sophisticated drawing of ripples in a pond. Even when you just imagine it or you see it, something about the ripples is that people always draw them equally spaced. And if you imagine the ripples or you look at ripples in a pond, you don't think necessarily about it like, oh, I'm looking at each one of those ripples. It's equidistant from the next ripple. But think of it in a different way. What you never see, but what you just take for granted. Well, I just take for granted when I'm looking at any kind of ripples. Again, just like tap the surface of the water in a bathtub. Look at any ripples that come out of your tapping, and you'll notice that you never see one ripple catch up to another. You never see one. I'm just going to write that down, in fact. And you never see them cross. Like, I mean, no. Yeah, I'll just leave it at that. You never see one ripple catch up or take over or pass another. Never, never. All the ripples all flow as one. That's what makes it a wave phenomenon, not just like, that's why any one of them is not a wave. The whole thing is a wave because so I'll just say, wait, it's like so poetic, it makes me sick. But no ripple will ever catch up to another ripple. The only way ripples ever cross is if they're actually coming in opposite directions. Then they do cross, and then really interesting things happen if you think about that, and we will. But unless if they're going in the same direction, they never pass each other because they're all going the freaking same speed, and the speed is fixed from the minute you say that water. If you know it's that water, they're going to go at that speed. That is an intent, and that includes. So this is why people say things like the speed of sound. Like, and again, I hate to emphasize, but if there's anything I can't emphasize enough, it's this. You've heard your life, your whole life, we've heard, not your whole life, I don't know, starting at some point in your life, we hear this phrase like the speed of sound. Oh, it's faster than the speed of sound. Oh, if you count between lightning and thunder, like you use the speed of sound to know how far away the storm is, which by the way, totally does work and is awesome and crazy that does work. But yeah, like and like you go to a baseball game, work with a stadium thingy, and someone's at a microphone way down there in the stadium, and you're way up in the cheap seats if you're a professor or whatever, and or you're in a Zoom session way up in the cheap seats, and like someone down there singing the national anthem, and like you can actually see their lips move before the words get to your ears, like a badly lip synced movie or something, because we all sort of know, oh, sound travels slower than light and sound travels at a speed. Why does sound travel at a speed? Like baseballs don't travel at a speed. Cars don't travel at, like cars can go any speed up to like 200 miles an hour. A baseball, if I throw it at 60, and for the throw, it doesn't maintain its speed even for one throw, nothing, right? Things don't go a speed, but waves go a speed. That's really crazy. There is a speed of sound, which is like a number. Now, if you, and what it means, and now here we go with the problem. Okay, so let's actually, okay, whether we finish this or not, this is now going to get us into a topic called, so what I'm talking about here is this, the takeaway, or the English point that I'm saying is the speed of a wave, which is omega over k, the speed of a wave pulse is constant and fixed by the medium. Like once you specify the medium, you've specified the wave speed, and it's not going to accelerate or decelerate, which means all easier physics applies, for good or for bad, or all more conceptual physics applies. We don't have to deal with acceleration. But also we know that the speed is fixed to the medium. You'll see, and remember, like all speeds are relative, all speeds are relationships. So what we're saying here is we have a relationship nailed down here that a pulse automatically comes with a speed that is fixed relative to its medium. Okay, that's what I'm saying in English. And where that, like, and it has enormous implications. Of course, it makes waves maybe sort of more easy and fun to study, but it also means something where I go, okay, back to this now. Again, even if we don't finish today, I want to introduce it. You're going to soon see it in lab. We're going to set up a situation. We're going to assume What we're about to do now is called the Doppler effect. It's based on what, like, if I really were a considerate person, I would stop and sort of just make sure, like, the takeaway for the moment is the speed of a wave is constant and fixed relative to medium. Like, it's fixed by medium and it's fixed to the medium. The medium determines the speed of the wave. If you change the medium, you change the speed of the wave, by the way. Sorry, actually, I'm going to add one more clarification. I'm going to try. I'm sorry, one more thing to make clear about that. I'm saying. Okay, two quick things. So just one is what I'm saying that, if you remember our old notation, the notation is starting to get clunky now, right? But it's necessary. First of all, remember our old notation that, like, if you put a zero next to something, then that means the value at zero, at time equals zero. So this v blah equals v blah naught is my way of saying v is constant. That may not really work for you. You may not love that naught there. You could do it a different way. But what am I talking about with this WM business? I'm saying remember, velocity is a relation, especially if you took 2 or 3, especially like at John Jay, it's emphasized for good or for bad that velocity is always a relation between two things. Nothing has a velocity. Everything has a velocity compared to something else, right? No one object has a velocity. To have a velocity, you need to have 2 objects. In fact, and so if you're really writing down velocities and being careful in a physics problem, you often have to specify with 2 subscripts what you're talking about. Like, there's a velocity of me relative to Earth, but there's the velocity of me relative to the sun, if you want to, account for the Earth, or there's a velocity of me relative to the subway, or there's the velocity of the subway relative to the ground, or there's the velocity of me relative to the ground. We have to specify, and we're going to have to. So I'm saying, what is constant here? What's constant for a wave is the speed of it compared to its medium, like how quickly the pulse ripples through the stuff. That's what's constant. And that thing is equal to wave, that thing is omega over k, but also the more common way to write it, especially in other science classes and stuff, that thing that's constant, so in other words, the velocity of the wave relative to the medium is the wavelength of the wave times the frequency of the wave. Like, yeah, okay, so who cares? Well, I care because it can get us into situations like this situation. Again, even if I've now maybe badly, wait, this class ends. We might be okay. Sadly, okay. This problem here, which I will now turn over to you, is an example of something called the Doppler effect. There are 4 common cases of this is true. The Doppler effect is a thing. It's a really nice thing in physics. There's 4 basic cases of it. You will end up knowing all 4. You will. Right now, I'm looking at one particular case of it. And and the common understanding, the typical familiar example of the Doppler effect is kind of like what I was saying before. If you're standing on the street and a motorcycle or an ambulance or a car or something goes past you and makes a noise, the noise is off. I think you're familiar. The noise can often do this funny thing. Now, actually, the noise can do like a lot of funny things. And it can get overly complicated by other factors, especially in the city. But here's what I want the part to focus on. Like if a car goes by you, if it's an ambulance or something, which is a very common version, of course, ambulances already make sirens that go like that already have like tones changing and stuff. So don't even forgetting about that. Let's assume that there's like one particular tone that's being blared by the ambulance, or just a car horn. Like if someone's just hitting their horn, so it's right, and they're coming down the street and they're going and they're coming toward you. What you might be familiar with, this thing that happens, and it does happen. It's like not a trick. Is as the thing's coming toward you, you hear, and then it passes you, and now it's going away from you, and you'll hear something like the tone will get lower. And obviously I'm, pathetic. And you may not, some of you have amazing sense of pitch, and some of you have less of a sense of pitch. I'm not saying that you sit there and you go like, oh, that's an A sharp. Oh, that's a B flat. But no, you just hear like, wait, can I just get a show? Can I get any electronic hands or anything, especially since I'm talking so much? Does anybody even like know what I'm talking about? That experience of like the thank you, Rain. You're the best. That's so fast. Thank you. Okay, yeah, all right, that thing. I'll just take Rain. Okay, so Rain. Oh, and Lloyd. Thank you so much, Lloyd and Rain. I'm telling you, yes. What is that word? Okay, God. We need. All right, I really need to stop talking. But that thing. And it gets, again, it's more pronounced if it's an ambulance or something, but any one tone will do that thing where it sounds one way when it's coming towards you and it sounds a different way going away. Now, that is called the Doppler effect. What the is of it, I have to explain, I have to define mathematically, but the is of it, the effect that I'm talking about, the part that your brain knows even if you don't ever think it through. When you hear, what's funny about it, not what's unusual or noteworthy about it, is like somewhere in your, even if you don't care about the person on the motorcycle, even if you don't want to think about the person in the car for 2 seconds, something in your brain recognizes like, well, there's no way they just changed what they were doing on the horn. Like it wasn't that the motorcycle like was going and then saw you and decided to play a different tune because of his overjoy or rage at you or something. So it had nothing to do with you that they started playing a different noise. It just all of a sudden sounded different to you. And so and that's right. Like obviously the motorcycle guy or person who's making this, the whole time they just hear, right? I mean, they're passing everybody. But the minute one of them passes you, you're, so it has something to do with frame of reference. There's something going on where he's in one frame of reference and you're in another frame of reference and you're hearing different things. And it's true. You are not hearing the same thing as the motorcycle. There's no way, because you heard 2 different things and the motorcycle's hearing one the whole time. So the Doppler effect in general terms is when the same wave, I guess I'll write this down in a minute, but when a wave travels from one frame of reference to a different frame of reference, so not just travels from one object to another, it's not when a wave travels from an object to another object and those objects are moving differently from each other. When a wave, and I will write this for you, but I'm just trying to give you the overview for anybody who's still left standing, sitting, crying, treating. When a wave travels from one frame of reference to another, so if there's any difference in motion between a wave source and a wave receiver, if there's any difference in motion, if the wave source and the wave receiver are not in the same reference frame, if they're not stuck together or moving together or stationary with, all this, if they're doing anything different, if one's coming toward one and one's going away from the other, then the same wave will be measured as having then the source and the receiver will measure 2 different frequencies for that same wave. And like all other things that happen due to frames of reference, they'll both be right. Like this is a frame of reference thing, where if you're in a different frame of reference from that which made the wave, you will you'll receive a wave that measures differently from the wave that was sent. And this happens prominently with sound waves. When it happens with any kind of wave, so okay, I'll write this. Hold on. Again, I'm going to ask you to solve this problem, but it's not really fair to ask you to solve this without me explaining it first. So one more. All right. This page, which I'll read out loud, this is the definition of the Doppler effect. This is the Doppler effect. Like, this is not an explanation for it necessarily, or prediction of the numbers or anything, but well, I guess I should make that clear. The Doppler effect always occurs if a wave is sent from a source to a receiver. If a wave, waves exist, waves get sent from sources to receivers. If and whenever the source of some wave and the receiver of that wave are not in the same reference frame, i.e., not fixed by the same velocity, then the source and the receiver will measure two different frequencies for that wave, and both frequencies will be right. To be super clear about the implications of this, and then we'll go back to the math. To be super clear, I'm going to go to the next page. Tell me if and when I shouldn't. And again, this is weird. I didn't mean for this to happen. I'm sorry, but the Doppler effect, I guess, I think it would just be torture to start solving the problem without me giving you this background. I don't, but it'll put you ahead. Anyway, oh yes. Now, the great thing about once you understand how a wave works at all is then anything that is a wave works like that. That's again why I love the equation. Anything that fits the equation then does everything we think the equation does. So now sound is everything we've been saying, we've been picturing like transverse waves, like ripples on a string. And by transverse, I mean we've been picturing this thing I keep saying, that like all the particles oscillate in the y-axis, but then the ripple propagates in the x-axis. That's just the easiest thing to picture, and it's just that. It's the easiest thing to picture and believe in. But what's totally possible and plausible and also happens all the time with the exact same math is you can have, instead of dy dt equals dy dx, you can have in effect dy dt equals dy prime dx, meaning that instead, if we were all thinking about waves, we could make a wave through Yankee Stadium by me standing up and then the next person standing up and then the next person standing up, right? And that would be a transverse wave. That would be when oscillation is perpendicular to propagation. But we could just as easily have me like push the person next to me, or like step toward the person next to me, and then the person next to me steps toward the person next to that, and then step towards, like same idea, right? But then we'd be sending a ripple in the same way. We each just vibrate, and a ripple goes. But there we'd be setting up nicely so that we get closer and further rather than just up and down. And so like everything's happening along the same axis. We compress and then we squeeze apart. We compress. Now that happens all the time in nature too. It's exactly the same math. It's just a little harder to draw or picture. And that's what happens through air molecules, and we call it sound. Okay, so sound, and instead of, well, yeah, so sound goes through air molecules. And once you know the temperature and the pressure of the air molecules, it's like knowing the K's over the M's of the little air molecules. Okay, I said that before. But so sound, I want you to believe, like sound is the real life example of everything we're saying. It travels from a thing to a thing at a certain speed that's fixed by that medium. The medium's usually air, although you can send sound through water, you can send sound through a guitar string, you can send sound through a drum skin, but you can't send sound through outer space, right? Like there's got to be something there that's vibrating. And if you send sound through water rather than air, it's going to change the speed of it. Like now it's different vibrating things. So it will act just like sound and do all the math, but just at a different speed. So like every different medium just fixes the speed. Okay, we said that already. So sound waves look more like that picture, not the other picture. But that doesn't, who cares? But now, once it's sound waves, you got these air molecules that are like packing, unpacking and packing and packing and unpacking, like compression, rarefaction, compression, high density, low density, high density, low density. That's what sound is. The frequency with which that happens, the frequency with which the molecules open up and close and open up, that's hits our eardrum. The eardrum vibrates at a certain frequency, and our brain, human brains, then interpret that. Well, first they change it into an electrical wave and then another kind of wave, like a lot. It actually turns into waves in all these different other medium, and the wave constantly changes its speed throughout our brain. But eventually our brain interprets that frequency as pitch, as the highness or lowness of a note, like kind of like tone. It's not exactly the same word, but like how far the keys are on a piano keyboard. Like so the higher the frequency of air vibration, the more you're, and many of you know this, then we're talking about like notes all the way to the right on a piano keyboard or whatever, or like thinner guitar strings or whatever. Frequency is pitch. But that's not to be confused. Where's the musical? I mean, everybody, that's as scientists or musicians or what speakers, we don't want to confuse highness of pitch or note or whatever with highness of volume, right? That's a different thing, how loud something is. Just to be clear, the frequency of the sound wave determines the note, and it's literal, like I'll be very specific about that in a moment. But the amplitude, like the height of the wave, ultimately, in fact, honestly, to tell you the truth, it's really the square of the amplitude, how high the wave is, that ultimately an indication of how much energy the wave is carrying, and the energy that gets distributed per unit area, per unit time, that's what then the brain interprets as loudness or softness. We definitely have to make this distinction, like in life, but in physics, and please stop me if this isn't clear, like sound waves are traveling along in the world. Sound waves are traveling along as in the form of air molecules getting closer and farther from each other. Well, okay, I will be specific. God, I cannot, I should either teach or not teach for a living. just to put it in real life perspective now, I'm saying when air molecules vibrate at a rate of 440 cycles per second, like literally, this is not just a random example or like and it is approximate in that I'm chopping off digits, but it's an exact number of digits that I'm chopping off. When air molecules vibrate back and forth at 440 times per second, then eventually that ripple goes to your ear. Then your eardrum vibrates back and forth at 440 times per second. Now your eardrum is now mechanical. It's like cartilage and stuff that you guys understand from other science courses, and I totally don't. But it mechanically vibrates back and forth. So now it's like a transverse wave in a different medium. Like your ear is not the same as air. So there's a different medium and a different wave speed now and a different even shape to the wave. But the 440 that was going through the air now is in your ear. Your ear, like part of your ear, is vibrating for real at 440 times per second. Now that creates an electrical signal that goes through your brain, an electrical current, which we're going to get to next. And the field of the electrical charge, well, the electrical field, which we have to talk about next, the implications, the consequences of that electrical current vibrate back and forth now electrically, okay, at 440 cycles per second. And eventually your brain recognizes that as the A that's in the middle of a piano keyboard. Like literally, again, this is not an example. This is actually like, this is a definition, and this is like Western music. And some of you already know this in a very bigger way than I do, and some of you don't. But like, like in other words, anybody who does have really good pitch, if they hear an A and they're like, yeah, that's an A. That's, oh yeah, that piano's in tune. That's a good A there, right? Or whether they know math or not, what their ear is recognizing is 440. What got preserved all the way from that note, like a hammer struck a string, it vibrated at 440. Then the air molecules vibrate at 440. Everything is different, string to air to then to your ear. All the materials are different, speeds are different. Nothing, no one object at all is going from any string through the air to your ear to your brain, but the thing that goes all the way through, the thing that gets carried from a piano that is in tune, or the person that hit the right note, the thing that goes all the way to your brain is the number 440. Like literally, like that rate, 440 is what travels. The number 440. I don't mean the freaking numeral like it's Sesame Street. I don't mean like a spongy, like 440 flying through the air, but I mean the meaning of 440. Somehow, what's known, what gets carried from that stupid piano string to the air, to the eardrum, to the electricity is vibrate back and forth at this rate, vibrate back and forth. Like that's the information that travels all the way at a speed of, in air, turns out, so this is a real number, approximately 340 meters. If the air is at standard temperature and pressure, okay, then compression vibrations will travel through air at approximately 340 meters per second, which is just under 1,000 miles an hour. Like it's fast and it's steady and it's reliable. What is it that travels? A frequency, okay? Frequency is pitch. And so then if someone hits, say, you know your favorite song, and maybe you think you don't know any music theory, maybe you think you don't know any math, but like, you know your favorite song, right? And you go and you hear some cover band play your favorite song, like a cover band, some other band plays it, right? And they're playing it. And then like, even if you think you don't play music, if you're just enjoying it, you know, if they mess up and they hit the wrong note at the wrong time or something, and you go, oh God, that sucks. Like what? Oh, I wish I were hearing the real band, or whatever the example is, or you go to chamber music, I don't know. But when someone messes up in music, any one of it, if they mess up enough, we all know it. Even if we don't know the letter names of the notes, and we're like, oh, that was the wrong note. Right? What does it mean? The wrong vibration number, the wrong frequency occurred. What we're receiving as frequency, what we interpret as pitch is frequency. What we interpret as loudness is amplitude, okay? Just bearing that, and amplitude you can change by giving more energy to the thing. But now, in the Doppler effect, yes, I see what time it is. In the Doppler effect, what I'm saying then is, somehow, when a car goes down the street past you and plays a note on its horn, and a frequency comes out of that note and then travels out of that horn, and the frequency that travels to your ear, something that we have to analyze occurs such that because you and the horn are in two different frames of reference, you receive a different frequency, or you'll measure a frequency that's different from the one that was sent. And that means you'll hear a note that is different because frequency is pitch. Now, I really will never shut up. It's easy to think with the Doppler effect. Many people think, oh, it's like as the ambulance gets, or as the horn gets closer to me, like it gets louder. Like, oh yeah, the Doppler effect is happening because the thing's getting closer and closer to me. Well, it's true that as something gets closer and closer to you, the volume that you receive will get more, like as it gets closer and closer to you, less and less energy of the wave is dissipated to the friction of the air. So yeah, you'll get a louder and louder signal when something's closer to you, but that's not what the Doppler effect is. The Doppler effect is not at all about volume or amplitude. It's about pitch. And the Doppler effect is entirely velocity driven. It has nothing to do with how far away something is. It has everything to do with how fast it's going. So here's now what I want you to picture. And I'm going to give you one more hint. I think realistically, even if we don't, I just want you to make sure you understand the problem. And then this is exactly where we'll pick up on Tuesday. If I actually put in the Google assignment portal, like finish this problem for Tuesday for credit, if I do that, then please do that. If I don't, then don't. But I do want to make, when I hit this on Tuesday, I want to hit it with a running start, so to speak. So I hope everybody can follow the scenario. The scenario is this. The scenario is this. We're finally going to analyze the Doppler effect now. We have two objects, a wave source called S, and we have a receiver called R. And the source sends a wave to the receiver. So it's like the car horn sends a car sound to you. We have a source and we have a receiver. And the source is sitting still in the medium. VSM equals 0, meaning the velocity of the source relative to the medium is 0. Meaning if we're sending a sound through air, the source, let's say now it's a parked car, is just sitting there playing the horn, sitting there, fixed to the earth, maybe, sure, but fixed in the air is what I'm saying. That the car is sitting there and there's no wind or anything like that. That's what VSM, and so be. Okay. So, sorry. Sorry. Great question. No, because so this F is meant to be a lower. Great question, range question. This, if we're talking about on this page, yeah, this F. By this F, I mean lowercase f. I mean frequency. So here's this is the notation I'm going to use from here on. By lowercase f, I mean frequency. And I mean like standard frequency. Again, like what comes out of the math of the differential equation stuff is like omega. But f means standard frequency, like hertz, like cycles per second. And lambda, that weird symbol right under the f, is wavelength. So Okay, so I'm using F to mean frequency, like hertz, like cycles per second. I'm using lambda to mean wavelength, so meters per cycle. So frequency is cycles per second, how rapidly. Lambda is meters per cycle. So again, by the way, then like cycles per second times meters per cycle, the cycles will cancel and we have meters per second speed. Okay, so V equals lambda F, but F equals means frequency, lambda means wavelength, and then from here on, like sometimes we're casual about the following, and sometimes we're not in physics, but we generally like to be really strict about the fact that velocities are relations, that any velocity is only meaningful insofar as it makes a comparison between two objects. So from here on, I'm reminding us I'm going to put subscripts back in our life. If I'm not going to write just V of just something, I'm going to write like VAB, meaning the velocity of A relative to B. Like anytime you see two subscripts, that's the two subscripts will refer to two other objects or two other reference frames with respect to which this velocity is being measured. So VAB means how fast A is going from the perspective of B. If B assumed itself to be at rest, if B was just stationary watching the world, what would it see A doing? That's what I mean by VAB. So thank you for, yeah. But now all the action here is going to be about a wave pulse. Like we used to talk about these velocities and stuff with objects back in Physics 203, but now we're talking about the motion of a wave pulse. So the setup is, and we may, again, it's becoming increasingly clear to me, we may get only as far as setup today, and I am a criminal. I mean, I'm not saying that on the internet right now. What I mean is I feel like, all right, anyway, what I'm saying here is, okay, we've got a setup. We've got a wave being sent from a source to a receiver. But I want to investigate a situation where the receiver's moving relative to the source, or you could say the source is moving relative to the receiver, or actually the better way to say it, and the better way I want to be clear is like they're not doing the same thing. That's for sure. That's what I want to look at. I want to look at a situation where like either an ambulance is going past a person or a person's going past an ambulance or whatnot. And what I really mean by that is where the source and the receiver are not doing the same thing relative to the medium known as air. So here's my specifications. Here's my given, my assume. And again, my main goal at this point is to make sure we all understand this setup so that we can dive in on it first thing Tuesday morning. My apologies for that. Assume this would be good with a picture, a real picture, not a stupid cartoon. I'm trying to make a picture in a second, but assume there's a source like that is stationary relative to the medium. VSM, I'm saying velocity of source relative to medium is nothing. The source is sitting there in the air. It does not observe any wind and no air molecule observes it going past it. All right, we're assuming that. We're assuming that the source makes a wave whose frequency is 500 hertz. Like that's a little bit above the A in the middle of a piano. It's more than an A sharp. It's like a B or a C, if that means anything. But it doesn't matter if it means anything or not. Just assume that a note comes out of the horn of some car that's sitting still in the air. And the note that comes out is like a 500 hertz note. That's a given. Now assume that that note, that sound, that pulse travels through the air as a wave pulse. And what I'm telling you is that the velocity of that wave, that sound wave, relative to the medium. So I'm looking at this part right here now. I'm saying assume that VWM equals 340 meters per second. In fact, I want to make it clear, like that's almost like this thing here, this fact. I'm giving this as a given in this problem, but this is like generally a given. This is like I think this color is too light, but this thing here, this 340, this is like a natural, but empirical. Like this is something we observe to just be true. At air, at this temperature and pressure, this is how fast compression waves move. Again, it's because of square root of omega over k and all that stuff, but like it's like a fact of nature on planet Earth that we use very, very commonly in science. So that 340 number, in other words, is not just a given of this problem. It like really is like a common given that the speed of, but what does it mean? It means the speed of the sound wave relative to the air through which it's traveling. This is the key to the whole thing. Even if, again, I've spent like, if there's going to be a punchline of this, is that if people talk about the speed of sound, what they're talking about is the speed at which sound travels relative to the air through which it's traveling. That's okay. So that's what 340 means, VWM. Then I'm giving you one last given to assume for this problem. I'm saying, or the character is giving me, VRM equals 50 meters per second. That means assume that the velocity of the receiver relative to the medium is 50 meters per second. That means assume that the receiver is moving through the air. Oh, wow. Oh, this is so awesome that you guys are actually, I cannot believe you're still paying attention. Yes. So, yeah. Exactly. Yes. Jerkel is the man and Rain is the woman and Lloyd is the man and we're all men and women. But yes. So what Jerkel just put in the chat, right? Like, in fact, yeah, I mean, in a way, we're done with what he just said. Like, there's a couple of things, and I definitely agree with it. And actually, the only reason we're not done, like in some ways, if you understand what Dirk Hell just wrote, in some ways, then you get the point of this. Like, yeah, when you run away from a wave, the wave is going to catch up with you less frequently than it was sent out. Like, I think that is what a big part of what Dirk Hell's saying, and it's like hugely right. In fact, yes, so much so. Let me say it again, that way. Like if you're at Coney Island or Far Rockaway, some beach, right, and there's waterways coming in, and you're standing there, you can either measure them very precisely with stopwatches and rulers and things like this, or just intuitively, like you're standing there and counting 1 Mississippi, 2 Mississippi. The waves are hitting you in the. Oh, yes. Okay, I want to continue this little scenario I'm saying, but boy, if you want to convince me that you were following, boy, yes. So what Robert just said in the chat, absolutely true. And oh yes, relevant. But definitely, in fact, maybe even meaning I am taking too long because yeah, we're going to use that very specifically in like a moment. It's the relativity of velocities and basically what the Doppler effect is the relativity of velocities kicking into action in the context of waves. Like anything, if you've ever thought that the relativity of velocities was at all interesting, or you felt you understood it at all in 203, or just this whole idea that we can be on the earth going and not feel a thing and be like, oh, that's ground. My feet are on the ground. I'm so stable. If like, I'm not Yaverbaum, I'm like so stable. It's terra firma. But at the same time, sort of in your brain also know or believe that terra firma ground is zooming past the sun at 65,000 miles an hour all the time. Like that's weird, very weird, but true, because that's the way velocities work, is that they're all just relations, right? So what this is going to be, absolutely, this is, if you've ever thought that was at all interesting or a thing, which it is, this is what the manifestation of that thing in wave context. So it absolutely, anything you remembered, like velocity of me relative to you is the negative of you relative to me. Like that's what Robert's saying. That is totally true. It's totally a big part of this. And we're literally going to use it in one moment if I ever shut up. No, we're not, because I totally didn't, because it's 1:30. Yeah. Well, so I'll finish this. So the thing we're going to leave, I'm going to believe now that at least 4 people really do know what I'm talking about, and maybe even want to, like, why are we even still talking? Like, I will show because I know it's 1:30, but like, what's the goal of this physicist? If Robert and Jerkel just like if they just tied it up with a bow and made you see what the phenomenon is, which I think they did maybe. And by the way, in sort of like go one step further, if you can imagine this phenomenon where 2 different observers will measure 2 different frequencies of the same thing. So like it's one note to me, it's another note to you. If you really understand that we're both right about that, then what that means is if you ever start believing, which by the end of this course, hopefully will, that light can behave like a wave, well then what happens is that light coming from stars to us gets measured as having one frequency by us, but measured a different frequency in the frame of reference of the star that sent the light to us. And I'm just saying this quick, just to put this in context, to show you that I'm excited that if at least 3, and I know it's more than 3 people, but if anybody's following this at all, what's big about the Doppler effect, it's not just that you can walk down the street and hear, and know that it wasn't an illusion. You actually heard that, but they actually heard something different. It turns out that the same thing happens with light in outer space coming from stars to us. The light that is sent to us from stars has a frequency as measured by them to be one thing, not that measured, but measured in their frame of reference to be one thing, and measured by us to be another thing. And with light, frequency means color. So we actually receive light. All the light we receive from stars, it turns out to be, in general, much closer to the red end of the spectrum than the violet end of the spectrum. It all turns out to be much lower. It all is measured to be lower frequency by us than it actually is as sent by them. And that is how we know the stars are, in general, on average, running away from us. Exactly what Durkel and Robert have put in the chat, and I'm sure, and Rain, in fact, like I'm sure other people are seeing. But yeah, like if you're, and this is the summary, and I'm sorry, and I owe you 5 minutes and like a lot of things, but if you stand at Coney Island and the waves are, you're like standing there, waves are coming in, blah, blah, blah. But then you start running away from them. Of course, they're going to hit you less frequently than if you stood there. And it's not an illusion. It's like true, right? They'd be sent out 1 per second. But if each one, as it's going toward you, you're running away from it, of course, they're going to hit you less frequently than they were sent. And if they're just water waves, you're like, okay, cool, whatever. If they're sound waves, like, oh, I just heard, eh. And if it's light waves, then we go, oh shit, those stars are all moving away from us. The universe must be expanding out from us. That's what happens. The Doppler effect, which applies to starlight and is then called the red shift, because all colors get shifted, is how or why we believe that the freaking universe is spreading out all the time because of this phenomenon. So I do think you understand. So I won't even, so the math, what's left to do is like to actually get the math. You have to get the numbers. Like how much does this happen for, like, how do you know how fast the universe is expanding based on what the frequency shift is? Like, so we have to do the numbers, but we'll do it next time. I'm sorry to talk so much. Happy Halloween. Be safe. Don't get something. I don't know. I'm happy. Cork bless America. If anybody gives a thumb or anything, I'm going to stop and post this right now. Could anyone say goodbye or anything? Or did you? Thank you. Yes. Happy Halloween. Thank you very much. I love it. Great. Thank you. Okay. Goodbye. You're the best. Goodbye. Okay.